Hello, am I audible?
Yes.
So, what about your examination registration that is done?
There is no response. In fact, I called Madam Bharti also,
Okay,
but she has not given any positive,
I
what you
think they will
say,
respond.
answer.
That's right. So, I mean, did you find the last assignments okay? Could you submit
Yes,
them?
yes, 80% I got, but now I cannot appear in exam.
Wait for their response. I don't know. Let's see. Anyways, if you study through these materials, then it will help because there are videos already. Later, also, if you are appearing, then this will help. Yeah.
No, but my question is, again, I have to appear in all this
I think
assignment or these
I
assignments?
think so. I'm not sure. I don't know about the I mean the regulations
See,
and everything.
these are all small, basic, what you say, queries. In
Hmm.
fact, NPTEL should answer that. Now, see, okay, there is error from my side. I missed that. But error should not be okay.
They should be responsive. That's right.
Yes,
So
but
you mail them. Yeah, wait for it, or you try to call them. See if they're
okay.
responding or not. That's the best thing you can do. Right. Uh, Fine. So I will share. The screen. I hope the screen is visible.
Yes.
So yes, as usually, I'll go through the course material. Then we'll go through some problems. So I think LQR controller, right? So have you gone through the lecture video? Because it is very involving. Hello, hello, am I audible?
Yes, yes,
Yes,
yes.
I'm telling. Have you gone through the lecture videos?
Yes.
So yeah, so basically till now, what we have learned is how to uh, stabilize a system. how to stabilize the system, how to analyze the system stability, and now you are going towards how to design a controller so that it respects some criteria that we want to impose on the system, and those criteria are mostly based on performance and safety. So uh, last week's lecture was regarding Lyapunov functions. How can we analyze the system stability based on Lyapunov in the Lyapunov sense, and how can we analyze system safety based on a barrier function, a barrier certificate. So using them, how can we design a controller? While we are designing a controller, till now what we have learned is we can place the wherever we want to place the poles accordingly by direct substitution method or Ackermann's method, right? We can design the gains for linear systems, but that is not always ideal depending on what is a designer trying to achieve. Usually the thing is the designer tries to achieve not only to stabilize the system but also to make it perform optimally. So when I say make it perform optimally, then the question of optimal control comes, and there is always a parameter that we are trying to optimize for the system, and this is how we consider that parameter. We call it a maybe performance index or cost, however you want to call it, and basically it's an optimization problem where we are trying to minimize this cost over a horizon. So here if you see, this is a control performance index that we're considering with J, and J is basically a function of x t0, u and t0. So basically x t0 is when I am starting from at t0 time, what is my state, and what is my control input, and when am I starting. So based on all these three, this whole performance index or cost is designed. So this is basically a function that we're integrating over time from t0 to certain amount of time, and t basically there is another function that is depending on the current final state. This is the final state up to which time we are trying to compute. Based on that, we are achieving a certain cost. So this is the cost to go basically when we are trying to reach to the final state, the cost for that, and this is the final state cost. So this is how the cost or the performance index, however you call it, is made, and optimal control tries to find such a control input, let's call it u star, basically, which is trying to minimize the cost function. So argmin j, so basically the arguments uh, using u as the argument, because u is an argument of this performance metric j. So for which u values at any time within this time range, uh, this overall j value will have a minimum amount. J will have a minimum value. Let's call it j star. So j star is basically something that is minimally achievable by this performance index, and for which u we can achieve that. That is what we are trying to find out in this optimal control. So obviously this is initial for any initial state, initial decision or remaining decision must be optimal. Yes. So these are pretty standard properties for optimal control, and usually we use dynamic programming approach to solve this, because as you can see, we need to know about the previous iterations up to a limited amount of time, obviously, and we'll see if we can reuse those data and we can reconstruct for the current state what should happen from the previous state. So it's a recursive problem, and we can use memoized version of recursion, and for that we can use dynamic programming approach. So these are pretty standard things. Yeah, this is uh, an example of quadratic loss or cost function, whatever you call it. So either we are trying to minimize loss or cost, whatever it is. Basically, this is a typical cost function that we consider, that is basically squaring both squared cost. Basically, this is a we are trying to find out a minimum from this, right? So and the final cost is denoted by this. Since we know where we are trying to reach, that in those states, what is the value of the cost. So if you are giving a low cost in that particular state, basically you are the control policy will always try to reach that particular final state where you have less amount of cost imposed. So yes, this is an usual system that we express as we are taking the dt part on this side so that we can integrate. We can find out a solution, and while you are trying to find out the solution, we are replacing that here while we are trying to find out that basically we are trying to find out the expectation of this noise. So we have noise right here. So this is basically the state, I think. Yes, these are a white noise basically. So this it has a mean value of 0, and it has a variance of certain amount that we are denoting with R1. So how do we express R1, and how do we express the whole covariance matrix for the matrix for the noise? That is how we are what we are defining here. So that obviously varies depending on how much my state will be varying. As much my state will be varying from the actual value, that is because of the variance of the noise. Because the noise is having a mean value of 0, that means mean value of this particular state at a certain time will be computed by this plus 0. But the variance, since these are not basically these are basically deterministic terms, but this is a probabilistic term or a random variable, so it will have a value within a certain range. From norm, it will deviate as much uh, denoted by this covariance matrix. So based on that, we can calculate how much variation is possible in the state, and we'll try to eventually minimize that. While doing so, yes. So this is basically the cost that we are trying to minimize here. Okay. So norm of x square, basically we are trying to convert it into a positive term, even if it is deviating from its reference. Consider its reference is 0, it is deviating in the positive or negative direction. You are considering that as a deviation in the positive direction only and squaring it, so that I mean, you have for a very small amount of deviation, you have a larger effect in the cost. That is why we are basically considering such a square term. You can take higher order term in case there are based on your need, you can design the control. So yes, uh, this is the loss function, and you are trying to find out within n iterations. Basically, when you are telling 0 to n h is your sampling period, and so you are saying basically starting from 0 up to n sampling periods, what is the total amount of cost and what is the expected amount of total cost. So yes, that is what you're trying to find out. And while you're doing so, I think QC is something a positive symmetric, positive definite symmetric matrix that you are weighting U with, I guess. No, this is the whole overall weight matrix. Okay. So this is the overall weight matrix. So this will be made for this is made for both X and U. Basically, same thing as we were doing here. Here we denoted it with R and Q. So there we are basically denoting the overall weight matrix for X and U. So we are basically considering this whole vector, that is basically combining the state and input vectors, and for all of each of the states and for each of the inputs, we are having individual cost in the diagonals of this matrix, and obviously they can have and correlated costs as well. Like for U1, there can be some dependency of X2 with U1, and based on that you decide how much cost it imposes and all. So yes, uh, so basically you are trying to do that for a discrete time system. So you are sampling the loss function at every sampling period, and you are trying to find out for which value it will minimize. And eventually you are trying to basically, I am not going into the computation, the calculations. I think those are very well explained in the lecture videos. Professor explained that very well, and in a thorough manner. So yes, so eventually what we are trying to find out is, in case of linear systems, what is important is what you're trying to find, or what we are finding out is, we are finding out the gain. not the u star only. We are finding out the gain that we will compute with the that will use to compute the control input. So the feedback gain, if we compute the feedback gain by minimizing the this quadratic cost, or you can consider any other cost. In this case, we are considering quadratic cost. These are same derivation that professor did in the lecture. I'm not going to that. So yeah, after minimization, basically you are finding out the gain and the solution of the Riccati equation. Basically, you are expressing the whole expression as a Riccati equation. Riccati equation as a particular format. Using that particular format, it is easier to find out what is the control gain. So look into the video. So let's do something like, let's solve a problem on this. That will help us understand what can I do. Uh, so consider first order continuous system that is represented by the following differential equation: x dot equals to xt plus ut. So we want to design a feedback controller such that ut equals to minus k into xt. So this is the k that we are designing within the optimal control, right? So basically we are replacing the u with k into x, and we will be designing, like, we will treat k as an unknown, and we will try to find out what is the k value of k. So you have seen that in the in the lecture video. So now let's find out. We want to design a feedback controller such that ut equals to minus k into xt, and desired equilibrium condition is xt equals to 0 at t tends to infinity. So basically 0 is the equilibrium point, or the reference point where we are trying to reach, where we are trying to take our state towards. So by imposing the control input, we are trying to drive that state towards this particular value. So that is what it means when I say this. So this is what kind of stability we learned that in our last class. Do you remember?
This is asymptotic
Yes,
stability.
yes, correct. So basically, asymptotically, we are approaching towards a certain value as the time is approaching infinity. So you are not telling how much it should decrease or with what rate. If we would have told that with what rate it is decreasing and moving towards the reference value, then it could become an exponential stability, maybe, depending on how you are expressing the change in the change of the state. Anyways, so what should be the value of k for the systems to be stable? So what do you think? What should be the answer? So let's see how to solve such a question. So basically, this is the system, right? So if this is a system, as I was saying, we know what is the control input equation. So let's replace ut with minus k into xt. So basically, this is what your system is following, right? This is the recursive equation and that your system is following. So your ODE is now x dot equals to 1 minus k into x. So I am trying to integrate that integrate it over a certain time window, maybe 0 to t. So basically, I am bringing the x below dxt, and when I am integrating, I am finding this. This is correct, right? I guess this is correct. Just check it. Let me know if you understand what I am trying to say. Is this fine?
Yes.
Okay. So as you integrate over time, you find this, and if you put the limits, and this is what you find out, and this is how you express xt. Does it not look similar? Where did we see this earlier? What does this mean actually? How is x0 decreasing?
It is decreasing. If that k is greater than 1, then it will decrease asymptotically to the x0,
Yes.
which is the initial position.
Yes. So basically, by putting k greater than 1, you are uh, not x0. Basically, it will decrease from x0. It will eventually try to reach 0. So the thing is, basically, if e has a negative power here, then it will become a fraction, right? So you are basically decreasing the values in every step, right? That is the idea. And so you know from here what should be the value of k if you want to make it stabilize it towards a certain value. So this is understandable. The questions will be somewhat, you have to think of it like this. And whenever there is a question in your tutorial, uh, in your assignment, you have to solve the questions in this way only. So this is one question and that I prepared. Some other question, I'll come to that later. Okay, I had this one also. Yeah, so consider the same system. Okay, same system, meaning the same system. Okay, xt plus ut and u equals to minus kt. Okay, consider same system and stability criteria given in question 3. Okay, the performance of the system is measured by the following loss function. Okay, so this is the loss function that we have to optimize in the optimal control. Till now, what have we done? We have not optimized any metric. So this is what we used to do while we used to find out by pole placement we used to design the control gains and everything. Do you remember? So this is what our goal was always. So make it stabilized so that our the eigenvalue is always within the unit circle for the discrete time system and in the left half plane for the continuous time system. So here it will be left half plane when if k is greater than 1, then this whole thing, this is basically the eigenvalue, right, of the characteristics equation. This is basically a minus bk, right? Do you understand what I'm trying to say? Here A is 1, A matrix. If you notice, it is one dimensional state, then basically A is 1 and B is also 1 and minus K is the only thing that is coming here. So basically A minus B into K. Do you understand?
Yes.
So if you try to find out what is the, depending on K, basically we are trying to, this is what we used to do while we used to do pole placement problems. Exactly this. So this has to be negative, right? So for that, we used to find out the case as that this is negative. So this is a very, trivial example, so that you understand what we used to do earlier, and this is what we do now. After learning this optimal control, this is what we are doing now. So yeah, now basically this is something that we have to minimize over time. So what should be the k now? Now m, there is an m. So x square plus m into u square. So if I think of it in terms of cost matrix, then what is the cost for my states? I mean q1, q2. Basically q1 is for q2 is sorry. Let me see. Q1 is for the so yes, okay. This is for the states. This is for the correlated cost between the state and the control input, and this is for the control inputs, right? So in our case, what is Q1 in this problem? Here, if I think of it like this,
It is 1.
yes,
It is
it is
1.
1, and for Q2 is M, right? So what is it asking? Given M is greater than 1, obviously more than the state cost, that is what it is trying to say. Compute K such that J is minimum. So we'll read the hint later. So yes, so we are not considering, we are making the problem easier. I don't have correlated cost between the x and u. So so basically q is a symmetric matrix because q12 and both are basically these transpose of q12. So the main diagonals are having the cost for states and the costs against the control inputs, right? So and q0 is something that we are considering the final state and input cost. So for this problem, what we have to find out is j is minimum. So I have given a hint. I don't know if such hints will be there in your assignment. Even if it's not there, so this is the idea you have to have, very trivial idea. With that idea you have to solve up to certain level, and you will obviously, if you have the options given, then it is easy to do. Eventually you'll understand what will happen. So here what we have to do, you have to compute j, and we have to find a derivative with respect to k, right? Why you are trying to, why it is saying that, what does it mean? Why do we need to find out the value of k for which dj dk equals to 0? Why do you think? So basically what are we trying to do? We are trying to find out where j is minimum, right? So at minima and maxima for any function, uh, what is the criteria that must be, I mean,
Differentiation, first differentiation is zero.
with respect to what? First differentiation with respect to what?
The problem which we have to optimize, like if we have to minimize j with respect to k, then dj by dk is equal
Yes,
to zero.
variable. So if we are plotting j with respect to the variables that it is built with, in this case the variables are x and u, and we are considering k also as a variable, right? So basically we have to find a minima for, so that this is basically we have to find a minima for j. It might not be the case that the minima for j with respect to k, x and u are the same, but since it is a one dimensional system, it's a very straightforward equation, and you are able to do all these things, because if it's a matrix, then basically you cannot do certain things that you can do for scalars. Anyways, here it's a scalar, so we don't have to worry about that. The question is simplified. I think if something difficult is given in the assignment, then at some level, at up to certain level, it will be made in a it will be simplified, I mean, so it won't be very tough, so that you can do it in hand. Anyways, so yeah, let's try solving this. uh yes, we calculated this earlier, right? Remember, right, in the last question. So let's replace it here, and by replacing it, we have to integrate it. Now we can integrate it, right, because the t variable is here, because this t variable there, we, while we integrated, if you remember, we integrated from 0 to t. So t is not a particular term, we are considering t as a variable. We can change the final time, that is what I mean by when I'm integrating with from 0 to a variable. So is this understandable what I'm trying to say?
Yes.
So here we are using infinite in place of, basically we are trying to find out at infinity what is the value that I am going to achieve eventually. So while I am doing so, let's solve this, and if we integrate this, this is something that comes out, and you are basically integrating this, and while you are integrating this is what you are getting. So putting the limits, and this is what you're getting. Is this understandable, this calculation
Yes.
that I have done? So it's very straightforward actually, but you just have to understand what to do in such cases. Always optimal control means this matrix that I'm giving has to be minimized. So that is the idea that I'm using here. So yes, this is the uh, j. Now if you see the j value, what are the arguments that I'm using here? What are the variables that are here? One, x. I have replaced u with x, so no more u. So m and k. So m I already know that it will be greater than 1, some value greater than 1. K I don't know. X0, is there any x0 given? I don't think so. Let's see. Let's see what happens. So if I find dj dk, so if you notice here, so this is an equation like it's like a parabola, right? Y equals to x squared, it's like a parabola. If you consider these are the uh, two-dimensional inputs of these functions, to the two-dimensional variables of this function, then basically this is a parabola equation. If you are plotting this and you are trying to find the minima, right, with respect to both. here with respect to k, but basically what we are trying to find out is compute k such that j is minimum. So we are trying to find out the k value. So we'll be trying to find out for which value of k j is minimum. That is what we're trying to find out, right? So here, if we do dj dk, this is what we get. Do you understand why we get this from this? Is understandable?
Yes.
Okay. So now, basically this has to be 0. Now, if you are equating this with 0, you are finding out that this is true. So now you notice that this is an equation of k, uh, quadratic equation of k, isn't it? So here you can find the roots of k by applying the Sridhar formula. So using that formula, you find out that this is the k that you get, right? So there are two possibilities. There are two roots, obviously, right? So what should be my answer here? Both of them? What should be my answer here?
Only dj by dk should be 0.
Yes, that is how we are finding out this equation. dj dk, we are trying to find out dj dk equals to 0. From this, we are getting a equation, which is basically a quadratic equation with respect to k. By solving that quadratic equation, we are finding two roots for k. Okay, using Sridhar formula, we are basically finding the roots of k, and these are the roots of k. Okay, do you understand what I'm trying to say? If you see
Yes, yes.
x0, it is not anymore depending on x0. If you notice, so this is what you get finally. Now, what should be, which option should be right here? There are
A,
two roots.
A.
Why? Why? Why not this one? Uh, why not C? Because I have two roots.
K should be greater than 1. In
Why?
that second root, K may be less than 1 then.
No, no. Why K should be greater than 1?
See, we have, since K is greater than 1, we have already taken that, na, in the previous question.
Yes, yes. So we have seen if K is greater than 1, then only it will become stable, right? Asymptotically stable. That is why you choose the value. See, this is always positive because we know M greater than 1, right? So this is always positive. Now we have to consider something so that k is greater than 1. Since this is always positive, the only way I can make k positive is if it's 1 plus this value. So this is the k that we choose. Is this understandable for you? Any doubts? Hello? Hello? Any doubts in the process or the solution? Hmm. So, hmm, okay. Now that we found out that how to get how to find out what is my optimal control gain, maybe linear quadratic regulator, we call it linear quadratic regulator gain, because the cost is quadratic here and the system is linear. So yes, what is the LQR gain here? That will help me uh, make a quadratic cost minimum. Uh, so this is not the only thing that we have to do, because this takes care of my performance, right? So my performance metric that I am minimizing, I am ensured that this performance metric will be minimized while I am using such a control gain that I have computed following this process, right? So I am computing each of the control inputs so that the loss function is minimized, and instead of computing this, I am basically computing k into x0, k into x1. So k is what I am computing every time. So yes, once you solve this, there comes another problem that this takes care of the performance, but what about safety? We learned about two things. So if you notice here, the cost function that we are considering here, it is resembling the Lyapunov function that we considered earlier, isn't it? Do you see the similarity? Why is, why is it so? Why do you think it is so? Any idea? Hello, am I audible?
Yes, sir. Yes.
So why do you think? It is clearly visible that the cost function that I'm considering, that is kind of similar to the Lyapunov function that we considered earlier. For we saw that for mechanical electrical systems, usually the kinetic energy will be considered as the as an ideal Lyapunov function candidate. For some, it might not be, but uh, usually it is like that for a moving mechanical or electrical system. Uh, so the thing is, basically, if you think of a Lyapunov function, so that Lyapunov function is has two parameters like this particular metric here. If you see the metric, it has, how many arguments does it have? I'll go to this definition. It has these arguments, right? So I am replacing u with k into x. So I have only two arguments left, that is x and t0. So initial time and x. So basically, this has two different arguments. One is time, another one is states. So if you think that as the time progresses, you want to design the control input such that eventually it is minimized, right? With respect to states, it should be minimized. Why? Sorry. So basically, you want to reach a certain reference value. So that particular reference value, corresponding to that value, you have certain v. So that is where you are trying to reach. And as the time progresses, so it is basically increasing. As the states are changing, it is basically increasing, or based with respect to x, it is decreasing towards a certain particular value, and that can be greater than the current value, or depending on where you are starting from. Maybe you are starting from 0 and your reference is 10. So you are trying to reach somewhere, maybe the Lyapunov function value is 100. Earlier we were in 10 0. So depends on that. Or you can find out, look at it from the other angle, that is like x minus the difference of x. You are trying to find out the cost by squaring the x into minus the difference, x minus the difference of x. In that case, wherever you are negating the reference with that, so that where always your difference is, you're basically shifting the whole x axis, uh, keeping the zero reference value, so that the reference is always at 0. So in those cases, basically it is a similar function like the Lyapunov function. So that is why here it is expressed with v also. So the cost to go is always I mean similar to the Lyapunov function. So you will see lots of similarity of the performance metric here with the Lyapunov function, where we are trying to find out a controller that is performing as we desire it to perform. But it does not ensure safety. To ensure safety, we need to add some more constraints in this optimization problem. So basically, this is an optimization problem where we are trying to optimize what? Uh, yes, so no, I go there. So basically, this is the problem that we're trying to solve. I'm coming to the start again. So this is the problem that we're trying to solve, and this is something that you are trying to minimize, right? So now that you are trying to minimize this has no constraints. Maybe there will be a constraint regarding what is the saturation level of U, what is the maximum value of U and minimum value of U that you can impose, and that will be mostly saturated depending on the K, because you are replacing U with K anyway, because you are replacing it with K into X and you are trying to find out the K, right? So while trying to find that out, you can impose certain limits on the U, but it will be automatically imposed from the limits of the X itself, if you consider equals to K into X. So here, let's consider a system like this. This is the same system that we considered. This is basically a continuous time dynamics of harmonic oscillator. That is a linearized version of it. I meant the system uh, in, a, in a linear and easier form, so that we can discuss about it easily. So anyways, the domain is this is the domain. Domain is basically where the states can start from, and this is the initial state space. That these things were already told in the last class. So this is how they are marked. Now, why I am considering a third dimension here? We already have two dimensions, and as you can see, it is a two-dimensional system, and we are having a third dimension here to plot the barrier certificate. Okay, so the barrier certificate is something that we considered, I think, in last class. Yes, so this is the barrier certificate that we considered in the last class. So if you see that we drew the circle, so we drew it on the 2D plane. Now if you see it in a 3D plane, you'll basically find out how useful this is in terms of control design. Why is this useful? Because we had how many, what are the properties that we had for barrier functions? Do you remember? Hello.
That it should be it should be inside the boundary,
What should be inside the boundary?
the variables
Which variables? The very
x1
specific
and
one.
x2.
So states.
Yes.
So that is an indirect, conclusion that you are drawing. So basically, barrier function is a function that is basically it's zero level set. What is zero level set? Zero level set of a function is basically the values of the arguments, the set of arguments of that function, inputs for that function, that evaluates to a zero value. That is basically zero level set for that. So zero level set is basically separating safe and unsafe property. This in another term means, for the safe regions, B will evaluate to negative values, whereas for the unsafe regions, it will evaluate to positive values. And that is how you differentiate between the safe and unsafe region. Is that understandable what I'm saying? Do you remember?
Yes.
Things are already taught.
Yes.
And that is where this criteria comes, and that is what you were trying to say actually. So since my safe states are negative valued, in safe states, I should be more specific in this case. So in safe states, the barrier certificate has a negative value or equals to 0. So basically, whenever I am inside this safe region, I have to ensure the barrier function has to be designed in such a way. We call it a barrier certificate only when its derivative inside the region is negative. And what does that mean? What does this mean, imply? Why does it imply this? What do I mean by invariant? Do you remember the term invariant from the timed automata class or the hybrid automata class? What do I mean by
The,
this?
the state in which it is there, it will be there, it is stable.
Not stable. We are talking about safety here, remember. It's a different
That
property
means
we are
the
talking
state,
about.
it will not change the state.
No, it is not like it will not change the state, but yes, invariant is something like that. No, what I'm trying to say is, if B is negative, If b is having a slope of b dot is having a negative value, then basically whenever you are starting inside this in the sublevel set of zero sublevel set. So sublevel set is basically, if z is my zero level set, then sublevel sets are basically all the values, all the x for which I am getting the v is evaluated as less than 0. So that is basically zero sublevel set. So the sublevel set, if I am starting from any of the x or states in the sublevel set of B, I will always remain inside the sublevel set, or I will always remain inside this inside the safety boundary. This is what it means. So if I am starting here, basically I will always move towards this. I will not go out and have a positive value. I will always move inwards so that I remain safe. So it is not like I will be in the same state. It is not like a steady state condition. It is basically a safety criteria. Do you understand what I'm trying to say? Is it
Yes.
clear now? So yeah, I think a trajectory example is given here. I mean, yes, it will be always moving inside this, not outside this. Anyways, that is how harmonic oscillators or pendulums come. So this is zero level set. So S is invariant. What does this mean? S is what? S is basically, okay, safe set. Domain set minus the unsafe set. So the safe set is basically denoted as S. So what do I mean by this? More specifically, forward invariant. Invariant is something that we used while we designed the hybrid automata and timed automata to ensure that the timed automata progresses, right? That is basically involved with the current state that I am in. I have to abide by certain criteria. So that criteria we used to denote with invariant criteria, right? Do you remember? For a certain location of hybrid automata or timed automata, we had invariants. That is basically a Boolean criteria that we have to always follow while we're in that particular state. So here I am saying when I am inside this, it is forward invariant. I should have written forward invariant here. So this means basically this region is forward invariant. That means as I progress in with respect to time, I always stay inside this particular region. So x belongs to S. This is a criteria that always remain, I mean, true while I'm starting from inside. So this is what this means. So this is understandable, right? What is what is the implication of the BDS certificate, design of BDS certificate? Hello.
Yes, yes.
Okay. So yes, now what we are trying to find out is we did not have this particular criteria in our optimization problem earlier. While we tried to solve the optimization problem and try to find out a certain k value. Now having a k value is very, I mean, for a linear system it's fine. For nonlinear systems it might not work because the the for nonlinear systems it is not easy to express as a in a linear form. So we are considering the linear systems, but we are considering a generalized version of the dynamical system, but in a linear form or affine form. We call this an affine form. Basically, this can be negative. This can be nonlinear in case of nonlinear systems. This also can be nonlinear in case of nonlinear systems. But for linear systems, we consider this as linear A and B. Basically, this is AX and this basically B into U. So anyways, F and G are globally Lipschitz. Globally Lipschitz means they do not escape uh, very fast. And do you understand what this means? This is important. Otherwise, system might not be controllable. So this basically means that if I have if I sample f or g, these functions at x1 and x2, and the ratio of x1 and x2 with the ratio of fx1 and fx2, it is finite, it is bounded. That means fx1 fx2 is not too much away from fx1, and that can be bounded by the difference between the x1 and x2. So if it's bounded, then only it is controllable ideally. So how much I mean, depends on what should my controller gain and everything. That is the idea of making them globally libshiz over the domain. Otherwise, I cannot control and design a control input if it's moving too fast and exponentially moving away from the reference value. So anyways, for this system, and existence of barrier certificate would mean this. So this is CU. CU is basically from where I mean the limited amount, like I was saying. This is the limit of the U variables. So this can be a rectangular box. We consider this as a, there is a like this is a space in this is my state space, right? So this is a two-dimensional state space. So consider there is another dimension for U, or consider a two-dimensional state space for this system has only one U, right? I think so. Only one U, I guess. Yes. So for this system, maybe it is one-dimensional. So there will be a range. You always should be within that range. So basically, it is trying to say various certificate exists means there exists a U control input such that this will be less than 0 for those U values, and for all B dot and X comma U, basically for all X, such X and U, this is true. And basically this would mean S is invariant. Is this understandable? This means basically you have designed a safe control input, that maintains safety throughout, and its derivative is also negative, so that it remains safe. So S is forward invariant. So this is understandable what I'm trying to say. This is a problem that we're trying to solve now. Is this clear?
Yes.
So like I was saying, the sublevel set of B equals to 0 is safe and invariant. So that is S. Smoothly deters the system trajectory to become unsafe. Discourage BXU for all X in D from becoming positive. So we'll come to what are the, so we have to impose certain constraint on the optimization problem that we were solving to design an optimal controller. And there, what do I introduce? Basically, control Lyapunov function. I bring the limit of control Lyapunov function here to understand how fast should I approach towards the stability, and I bring in an idea of the CBF, control barrier function, to understand how should I maintain safety. What is the, so idea of CLF? We have read about Lyapunov function earlier, so we are using it here. Earlier in optimal control, what we were doing, we are trying to only minimize a certain amount, a certain metric. We are not telling how should the state be decreasing and with what rate the state should be decreasing and everything. But here we will be deciding exactly with what rate it should be decreasing, or that means basically how it should perform, how fast it should decrease, or how fast it should approach. We are not only talking about asymptotic stability here. We are now moving towards exponential stability, which is a stricter performance requirement for controllers. So this is to impose an exponential stability criteria or a decay rate, desired decay rate on the control while it's trying to stabilize the system. And the CBF, control barrier function, is being used to impose certain safety property and how fast it should remain, it should move towards safety in case of corner conditions where it is going almost towards the unsafe region. So how fast should it come back? So basically, this is a Lyapunov function. It is continuously differentiable. We know the properties of, what are the properties of Lyapunov function again? Like barrier function. Do you remember? Hello.
Yes, sir.
So what are the criteria of Lyapunov functions?
It is symmetric.
Not symmetric. If depends on what is the power of u x. So usually it's positive. If it's even power term polynomial, then obviously it will be symmetric. Anyways, not only symmetric, it basically criteria are. Hello, your
It is
voice is breaking. Your voice is breaking. Your voice is breaking terribly.
defined matrix.
Sorry.
PSD, positive defined.
Positive semi-definite. Yes, positive semi-definite and symmetric. That is not V. That is P. If we consider P as the coefficient of a quadratic equation, and then P comes into the picture. Here we are talking about the property of the Lyapunov function V. So at equilibrium point it should be 0, right? I'm reminding you again. So other than that, it should be always greater than 0 in anywhere else in the domain. So with respect to x, it is always increasing, as I was saying. So and with respect to time, it should be decreasing towards a certain value, because it should decrease eventually. Why should it decrease? It should decrease towards the equilibrium state. So anyways, so this is what you get when you do a derivative, I mean multiply. uh, so how do we get this? Let's see. So this is some criteria that will eventually impose in the control problem that we are going to solve, optimal control problem that we are going to solve. These are criteria that we will be using. So basically a control strategy based on CLF that ensures exponential stability with gamma decay rate is KCLF equals to such a nu within the range, obviously allowed range, that has this property becoming always true in the domain. Why this property all of a sudden? So if you notice, this property is nothing but V dot. Do you remember how should V dot behave for a Lyapunov, for V to be a Lyapunov function? V dot should be what?
Less than 0.
Yes, less than 0. But here we don't only stop with less than 0. We are not happy with less than 0, because that is for asymptotic stability. Here we are making it as less than some minus constant scalar term and multiplying it with its own value. So this is basically a recursive equation, right? Recursive inequality. So here, if you notice, this is how it will decrease. Okay. So making this decay stricter by bounding the decay of CLF with this, that is this. So this is what we are going after. Now do you see, V dot less than equals to minus gamma into V. So this is exponential, isn't it? If you solve it by integrating both sides, like we solved the x dot equals to some value. Do you understand why it is exponential? You will have something at V t equals to 0, the value of V, and eventually as you are uh, I mean approaching the next states at x equals to 0, whatever V you had, and along with that, as you are approaching, what is the value of how the value of V should change, that will be decided by e to the power minus gamma, right? Do you understand what I'm trying to say? If you solve
Yes.
this, you'll get that. So with that, we are basically restricting the rate of decay of the system state as well. So indirectly, we are basically restricting the telling the system, telling the controller that I'm designing, that how the system state should decay. So now if we are starting from here, see, this is the sub-level set of initial x. So basically this is where I am starting from. Okay, this is where I'm starting from. Okay, so consider this is a projection. Basically, this is my state space. This 2D x1, x2. This is my state space. This is a pendulum harmonic oscillator. This will be moving like this only. So I'm starting here, and eventually, if you see, this is the sub-level set of where I am starting. If you see, this is the ellipsoid or circle, whatever you call it. From boundary of this, I am starting, and I am always going inside and towards this equilibrium problem, equilibrium. Now, in this case, equilibrium can be this or this, depending on the equilibrium. We are moving towards the equilibrium, but I am always rolling down the slope of the Lyapunov function. Is this clear? What I'm trying to say?
Yes.
But if you notice, this does not ensure the safety, that I should not reach the unsafe region. For that, I bring the idea of this control barrier function. So what do I do here? We basically introduce a new function. Here I am considering another lambda that is also kind of a decay rate. This decay rate is imposed whenever I am reaching very near to the boundary, safety boundary, forcing invariance on reaching zero level set. So whenever I am reaching this boundary, I am very near to the boundary. Basically, this is how it is trying to minimize me. So allows b to increase as long as b less than 0. So if you notice this, you will see if b is inside this, then basically you are allowed to increase, right? If you put a negative value here, do you see? Do you understand what I'm trying to say? If you put a negative value of b, you are basically bounding the slope of the increment of b. That is a barrier certificate. Okay. But when you are reaching a positive, where about to reach a positive value, basically you are bounding and trying to make its slope negative. That means you are asking the system to come inside, stay inside the safe region. Do you see it from the criteria that I presented? Hello. Hello. Is there a problem to understand?
Repeat your question.
I am telling that, do you see when the b is a negative value? When is b negative? When I am inside the safe region, right? Then
Yes.
this slope of b will be bounded by some positive value. But when I am almost becoming coming towards the zero level set, I am trying to bound it more. And when I am becoming positive, almost about to become, cross the zero level set, then it is basically trying to make my slope negative. This will be negative then. So basically, I have to turn back and go inside. Do you see? That is what I'm trying to say.
Yes, yes.
So that is how it is, different from the Lyapunov function. So here solely my goal is to keep the system inside the safe region. That is the goal of my design. So this is basically bounding the positive slope of B in sublevel setup. So yeah. So if we see now, this is the design criteria in this case. So I am trying to find out. I am not going to the definition of it. So this is basically b dot again, like that was v dot. This is b dot considering the new representation of the system. Okay. So basically you have to do dv dt. So you make it dv dx and dx dt, and dx dt is something that you replace with f into f of x and plus g of x into u. You understand that, right? I mean, how we are getting this? I mean, this left hand side thing. Hello.
Yes, yes.
Okay, fine. So now that we have this, this is the final problem that we are going to solve to design a safe controller gain using CLF and CBF for optimal control. And in this case, again, I have some cost. I am thinking that cost looks like this. It can look like anything. Basically, there we saw some cost on the states of the system also. But here, since we are considering the exponential decay, so we can decide any cost function. So here I am considering a slack variable, if you see. So delta. So maybe for strict conditions, if we put this as constraint along with this as objective, so this is the objective function that we have to minimize, and we have to find out such u values at every instance. At every instance, you have to find the u value so that this is true, the system is safe, enforcing safety, and this is also true. That means basically the system is performing with the particular desired decay rate. Okay. So this is a slack variable that we are adding here. So basically, see, this is basically relaxing the problem. We are not asking it to be more negative. we can relax it a bit, and so that we relax as less as possible, we are adding it in the objective as well, so that when I relax the minimum, then the cost is also minimum. So this is the problem that we will solve. And this is understandable what we are, how we are getting this and how we are getting this and the objective. Hello.
Yes.
But if you see that for safety, safety is not something that we can relax, because safety criteria is very stricter, stricter criteria compared to the stability criteria or performance criteria. So if we are not inside the safe region, I mean, we should not choose that particular control input at all. Okay. So that is very strict criteria. So we are not adding any slack variable to that particular constraint. We are very specific about that. Anyways, so here is an example of a system. For this particular system, again harmonic oscillator system, and it has only one input. So for this system, this is the CLF that we are considering. This is the new CBF that we are considering. So with this CLF and CBF, if we are designing, so this is the I think barrier. I mean, this is the unsafe region, and if you see the trajectories are moving like this, always avoiding this. Now for another system example, ACC, that had that kind of equation. It's not. It's basically f of x plus g of x into u. So this is somewhat linear. This is also linear, it seems, depending on v. No. So yeah, linear only. So yes, fx plus gx into u. So you have the values, you have the v control Lyapunov function, and you have the barrier function as well. So this is how your barrier function looks. So what does this mean? This is the state space. D and V are the two states. If I have the barrier function like this, what does this mean? What is my safe region? Can you tell from the figure that what is my safe region here?
The triangle, that the 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 area which is below this quadrant.
Not quadrant. I am asking you to kindly use this particular term, because that is important. Zero sublevel set of this particular function. That means this is a zero level set, this parabola like structure, right? This is a zero level set, right? Where the function
Yes.
is evaluates to zero. So below this is the safe region inside this, basically, right? Is that clear what I'm trying to say?
Yes. Yes.
Okay, so if you plot it, you will see eventually it is reaching to, I think 14 was the reference value for speed, and the controller was designed to reach a certain reference velocity, because it is ACC. ACC is basically you are trying to find out a certain, I mean, uh, trying to find out the acceleration so that you reach to a certain velocity, and the velocity, reference velocity here, it is 14. So trying to reach here. I think this is Z distance. I think this should be D, I guess. Anyways, so this is the other state. So the other state eventually is going to zero. Desired spacing from the lead vehicle. So you have some desired spacing. So this is the difference from the desired spacing. So you are reaching towards the desired spacing. If your desired spacing is 20, say, so you are reaching 20. You are deviating less from the desired spacing. So this is how you choose your control inputs, and this is the slack variable. If you see, slack variable value is increasing as the time is going, so it is harder to find out a control input that is satisfying all these criteria. So here, if you see, here is a CBF value. It is almost reaching zero, but it is remaining safe. It is not going beyond zero, and this is the CLF value that you see. So yes, it first decreases, and it is struggling to find a suitable control inputs, so it's increasing the slack value, so CLF is also increasing because you're relaxing it, right? So anyways, so based on this, if so, there can be questions regarding what should be showing such a system, and this is the function, and this is a barrier function, and all these things. What should be, what is the I mean the safe region, or what should be the, I mean stability criteria, or something like that, showing the system equation and the figure of the CBF or the CLF. These things can be asked, but mostly they won't ask you to derive the CBF or CLF, because that is not very easy problem to solve. So usually this will be given, and based on this there will be questions asked. So which of the following is invalid constraint for designing a CLF-CBF based optimal control strategy that outputs the optimal control action U for a dynamic system x dot equals to this, such that this is minimum for a positive definite symmetric. So which one is not correct? Invalid constraint. What do you think? And why so? Why D is not a valid constraint? What do you think? Hello, am I audible?
See, in that, because in the barrier function, there is no relaxed condition. It is only with
Correct,
that.
correct. So you have to be very careful when you are imposing a safety criteria while you are designing the controller. That has to be very strict. So yeah, another question can be, which of the following are true, as we say uh, a set S is invariant for a dynamic system state vector X. So what does this mean? I mean, which one is true when we say that S is invariant? I just explained it. Which one do you think is true? Sorry, your voice is breaking.
D, answer is D. Okay.
Why did you think it is D? Tell me.
See, D, because that condition at 0 is T0 is 0. That is also one of the condition.
No, that is not. Why X has to be 0? Why should I start with 0 always? I can start from anywhere in the safe, I mean, my domain, right? You are confusing with the Lyapunov function and the actual system state. Here X is system state. It is not Lyapunov function. Lyapunov function should always have a 0 value at the equilibrium point. So S is an invariant region. That does not mean that you have to start always from 0. You can start anywhere from S. If you start from S, you always end up in S. That is the invariance. Do you understand?
Yes, yes.
So be very clear about things. Why this is not true? Why B is not true? Hello? Why is B not true? Hello? What does this mean? And what does this mean?
First one is for
This is
all T. Second is there exists a T.
why this is wrong and why this is right. What can you say by saying this is right and this is wrong? What am I trying to say here, convey here, when I say this is wrong?
In this B, B may be 1 point, but for what you say A, it is a continuous time.
Basically, it is saying, it is not imposing that always I have to be inside S. Like we impose while I am in a location, I have to abide by this particular criteria. That is invariant, right? Invariant logic. So here I am telling there exists some time where I will come back to S, but that is not what we are trying to say when I am saying S is invariant. And this is also not true, not completely true actually. So there has to be a antecedent. This is the antecedent that I start inside S. If I start outside S, this is not true. If I start inside S, then I always end up inside S. And that is what is called invariance. So yeah, these are the problems that I prepared. So do you have any other questions regarding this week's lecture? If not, then I'll end it here.
Sir, how to, what you say, we are understanding, but it is not able. See, I cannot retain this. Say, I'm trying to get, but all the things what we have learned, how to memorize. That is a little bit problem I am facing.
Memorize what?
Memorize the concept what you have told now. See, like
Okay.
understanding,
So
but how everything how to summarize and keep intact like you do.
okay. So where did we start from? Let's try to summarize what we have done so far. We are here, right? So
Yes.
here, and these are the things that are left. So we started from all possible CPS components, sensors, and everything. Then we focused on some components like the operating system or the real-time implementation of the control task, how to schedule them and everything. While doing so, we saw that there is a timing criteria that is coming into the picture. So there we learned about all the scheduling policies and everything, different scheduling policies. For them, what are the communication policies? In communication policies, there will be different algorithms. In processor task assign task scheduling in processors, there are different algorithms. So both of them we have learned. So for both of them, one thing is very common that you will see, that you have to compute the uh, worst case response time computation. That is common for both. To remember, for
Yes.
communication network or for processing inside processor bus network, for both that is very important. So that is something you have to be very good with. You have to go through those things very well when you are preparing to the exam. So practice them very well and know the algorithms and why which one is good and which one is different from the other one, how, all these things. Then comes, since there is a timing criteria and all these things, then we see in plant side we focus on these two main components, controller and the plant and the communication medium between them. So these are the main three components that we will study in this course. Now that we come to the plant design and how we analyze the plant and design a controller for it, there we analyze stability. First, for the continuous system, very typical criterias, and you just have to remember, and those are, I think if you know control system, then it is very straightforward, these things. And now if we are coming to something that is very much implementation specific, that is reliable design in the platforms and still maintain the stability of performance. So that comes from the fact that during scheduling there can be sensor to actuator delays. Why? Because it takes the computation time depending on the controller design where I am implementing it, depending on the platform, it takes time. So based on that, how can I change the actual feedback closed loop equation based on how much time I am taking in the platform, and based on that, how can I maintain stability? If there are certain misses, if I miss certain deadlines, how do I maintain stability? Okay, now that I have designed these things based on the plant, analyzing the plant, I have designed the basic design of the control software is designed, and that is also platform specific. Now you have to verify the system, if the system is safe or not. So here it comes about hybrid automata. Hybrid automata is something that helps me model the hybrid nature of the CPS, like continuous plant and discrete controllers, right? So along with that, we can verify against certain safety property by expressing it in terms of hybrid automata. and that is where I get the idea of reachability analysis along with that SMT based verification, right? We are doing nothing but we are trying to express the how the system is behaving, evolving in the closed loop for a certain amount of time. That is what we are trying to find out. So along with that, we are basically finding out if there is a certain safety criteria, if I am considering a region where I am reaching after T amount of time, if there is an overlap with the unsafe region, or I am trying to find out if there is a satisfiable solution in the SMT formula when I'm expressing my evolution in terms of some formula. So basically these two, while reading these two, you have to understand how to design such an automaton. And if I talk about designing an automaton, it can be timed automata or hybrid automata. The invariants and the guard conditions and the resets, how to design them, those logics are very important. So you have to understand that, because based on that only we will eventually verify, because whatever our criteria are, that will be imposed by those guards, invariants or resets on. So that is something you have to learn how we are designing it. So go through the examples in for these two topics and learn how we are evolution of the system for the bounded amount of time. How is that being expressed? That is very simple. Once you see, if you go through my lecture also, there I segregated things: initialization, then progress, then guard. If I am changing or not, I have to change the location or not. If I am changing location, then check the invariant. Always keep on checking the invariant when I'm in the location. Based on the sampling period, you check once in once in your sampling period. So like that, if you have to keep on checking, and eventually when you stop, you have to see now, do I overlap with the unsafe criteria? So you are given a safety criteria, negate that. So you get an unsafe criteria. You try to find out if there is a satisfiable solution to that. And if you are doing disability analysis, then basically you try to find out if I am going to a region where I should not go. So this is done. Now I have ensured the safety of my system design. Now comes the performance while I'm designing the control. So here we bring in two concepts: Lyapunov stability and barrier functions. So if you understand the how the Lyapunov function is designed and how the barrier function is designed, how they are defined, then it becomes very easy. The next thing that you have to understand is how LQR controllers are designed. So if you understand these three things for these two lectures, and when I'm telling understand, I mean to say that when a professor has done the LQR, how the LQR formula is derived, solve that in hand while it is done in the lectures. Try to do it by yourself as well. And along with that, what are the constraints that I am adding to make it safe? These constraints depend on very much depend on the idea about the Lyapunov function and the barrier functions. So if you understand this, what are the criteria of the Lyapunov function and the barrier functions, you can easily add these criteria to the optimal control problem, and you can easily find out. Basically, based on the safe control design, there will be theoretical questions mostly. If there can be some questions like they can show you for this system what is a safe region, and this is the control design, this is the barrier function and Lyapunov function, will it be safe or not? Usually candidates will be given. That is how it will be usually. And after this, whatever is coming, you will see. So this is the summary, and this is how you, put importance on things while you are reading each and every chapters. Does that help?
Yes.
So yes, go through them one by one, and let me know if you get stuck in between. Fine. So I'll end today's lecture here. Any other questions?